just about right.
Okay, so once I have a valid inner product, then I have all these geometric notions at my fingertips. Things like angle between vectors, norms of the vectors, things about perpendicularity, right? We have the Graham-Schmidt process to take a set of vectors and turn it into an orthonormal set or an orthogonal set. All of those things, this is all from sections 4.11 and 4.12. They all come into play once you have an inner product defined on your space. So we can't really visualize this angle because we're talking about vectors that don't really have pictures that go with them very, very nicely. But we can still define the angle between these two vectors. So does anybody remember the formula for the cosine of the angle between two vectors? Think a little bit. It is. It's inner product, you can't, so inner product of f doesn't make sense, right? It has to be inner product of f with some other vector. You thinking of the norm? That's part of the formula. You know what it is, Israel? No? Does anybody know? Justin?
The inner product of f and g divided by the norm of f times the norm of g.
There we go. That's it. Okay, basically it's the same formula that you learned in 250A, except instead of a dot product, now I'm writing it as an inner product. It's the same concept. Okay, and remember that the norm of f, right, is the square root of the inner product of f with itself. So we have to calculate this thing. So this is just the square root of, let's just go ahead and start doing it for this particular problem. So it's the square root of the integral from 0 to 1 of t times f of t squared. So f of t is going to be 12t squared, and I'm squaring that. So all of that is underneath that radical. So you're just going to have to carry the square root sign all the way through everything, right? So this is the integral from 0 to 1. It's all underneath the radical. Integral from 0 to 1. If I square that thing out, it's 12 squared is 144. How many powers of t do I have here? 5 of them, right? By the time I simplify that thing down. And now I'm integrating t to the 5th, which is 1/6 of t to the 6th, right? Which I'm then going to evaluate from 0 to 1. So if you take 144 and divide it by 6, you're going to get 24, I believe. So there's the answer. The square root of 24. So t to the 6th over 6, right? The over 6 part cuts 144 down to 24. And then t to the 6th gets evaluated from 0 to 1, just give you 1. Okay, are we good with that? So that's the norm of f. Now we also need to find the norm of g. The norm of g, give this one a try real quick. This is going to be the square root of the inner product of g with itself. I'm going to try and do this one fairly quickly. It should be fairly easy. The integral from 0 to 1 of t times the quantity 2t squared. And so now I'm integrating from 0 to 1 of 4t cubed, I believe. Which is going to actually just give me 1, right? T to the 4th, the value from 0 to 1 is just 1, and the square root of 1 is 1. What do we call a vector that has a length of 1? A unit vector. And in fact, if it's a unit vector, then if I'm normalizing, remember you can take vectors and normalize them by dividing by their norms. So I could actually, so for example, g is already a unit vector. I could make f into a unit vector by simply dividing it by the square root of 24. We're not asked to do that right now on this problem, but that's something that you can do. You can normalize your vectors. So, so we've got the norm of f and the norm of g, and now we just need to check the numerator part, right? The inner product of f with g. So let's do that here. The inner product of f with g is the integral from 0 to 1 of t times 12t squared times 2t dt. Right? And it looks like I can pull a 24 out of that, and then I'm integrating t to the 4th. When I do that, I'll get 1/5 of t to the 5th, and when I plug in 0 to 1 for my limits, it's just going to give me 1/5. So doing it kind of quickly, because it's very easy. That's going to be the formula. So cosine of theta would be 24/5 over the square root of 24. Or in other words, it's the square root of 24 divided by 5. There's the cosine of theta. That's less than 1, by the way. Always has to be. The in any inner product, you can prove, we didn't really do it in class, but I think I stated it, that the denominator is always bigger than the numerator. So. Okay, so that's good. So we did that. I'm really doing pretty good here. I have a couple more, maybe, and we're not too far from being done what I want to do. Are there any questions on this?
You're most likely going to be asking us questions like normalize or polynomize, things like that.
Yeah, in fact, one of the next ones I was going to do is one of those.
Okay.
I was going to do it second. But yeah, the Gram-Schmidt process would be something. The Gram-Schmidt process is where you take a set of vectors, you orthogonalize them by using the formulas. Now I'm going to give you the formulas. You don't have to memorize those, but you do have to be able to go through the process. Once those vectors are orthogonalized, then you can, then you can normalize them by dividing by their norms. So that's pretty easy. So let me come back to that maybe. What I think I was going to do first is ask you a couple of sort of a series of theoretical things real quick. I will be asking you some theoretical stuff on Monday, and I haven't practiced a whole lot of those yet, so let me just, this is number 8. So in theory there were 11 new problems, so how did I manage to cut down to 8? Oh, it's because I was going to skip these other. There's a couple others that show that this is not a valid inner product or whatever. And it's actually something that I think basically was in the homework more or less. So I wasn't going to do that one necessarily. Yeah. I'm actually although it's number 8, I'm really on number 9 because I incorporated one of the other problems into another problem. So actually doing pretty well here. So we'll do a number 8 and a number 9, and then call it a day. I feel pretty good. Like I feel like we've covered a lot of stuff. We haven't covered everything. Certainly haven't covered everything, but we've certainly talked about a lot of things. So that's certainly good. So here are some sort of theoretical problems. Give, and you may have seen some of these before, but that's okay. Give an example of diagonalizable matrices A and B such that A plus B is not diagonalizable. So we're being asked to give an example here. It means there's lots of right answers, lots of things you can do. We're talking about matrices. So if we're going to give an example involving matrices, what would be a good size matrix to work with?
2 by 2.
2 by 2, I agree. So let's try a 2 by 2 matrix. Does anybody have any circumstances where you like know immediately that the matrix is diagonalizable? Because wouldn't that be nice? You don't have to like actually calculate the, you know, the details of the eigen. Remember, diagonalizable just means every eigenvalue holds its weight. But to really check that, you have to go through the null space stuff and see how many free variables you get and all of that. That's a little bit more grunt work than we want. Is there a way that we can just, do we have a method of just writing things down and say, yep, I know that's diagonalizable?
Upper or lower?
Okay, upper or lower triangular is great. So let's do 2 by 2 and let's make it upper triangular just for the sake of discussion. Why does upper triangular help make this an easier thing to do? Right, the eigenvalues come out just right on the main diagonal. And if I want to make A so that it is definitely diagonalizable, what would I want to do with those diagonal entries? Make them not repeats, right? So what, Nathan, what are your 2 favorite distinct numbers?
1 and 1.
Okay, doesn't matter. As long as they're 2 different numbers, right? I already know that this matrix is definitely diagonalizable regardless of what I put in the upper right corner, because my lambdas are going to be 1 and -1, and so they're going to pull their weight. Okay? So I need to still fill in that top right corner, but let me do that maybe in a little bit. Okay, so I need to come up with a second matrix that also is diagonalizable. So let's once again make it to be upper triangular so that we can control its eigenvalues. Does anybody have a suggestion of what I can put here and here?
7.
You want a 7 here?
Yeah.
And what do you want here?
93.
93. Okay, great. I love it. So there you go. And we're still not quite filling out the whole matrix. Let's say we do that. Now let's look at A plus B. Of course, we're going to get a 0 in the lower left corner. And when I add the entries that I've written down so far, this is what I have. So is this going to work for us? We want A and B to be diagonalizable, but we want A plus B not diagonalizable. So far, how's it looking down here? It's looking diagonalizable because I have 2 different lambdas. So Everett, could we get some different favorite numbers for the diagonal of this matrix? Sorry. You need to burst your bubble there. They are. Let's change the 93. What can I change it to? What should I change it to if I want to make this work? 9. Why 9? Because now when you add, you get the same number on the diagonal, right? Okay, so you get the 8 and the 8. Now we want this one, these 2 are already diagonalizable. Is this one definitely not diagonalizable? Or is it maybe? It's maybe, right? If the eigenvalue is repeated, it doesn't necessarily mean that it fails to be diagonalizable. So what kind of a number do we want to get up here? Does anybody? So if you think about it, when we look at A plus B and we do this eigenvalue, right? We're going to look at the null space of what we get when we subtract 8 from the main diagonal, right? And if this question mark happens to come out to be a 0, that would actually be bad, because that would mean that there are no pivots, which means 2 variables are free, which means that I can get a 2-dimensional null space that pulls its weight. So you want to get something here that's not a 0. Can we make that happen? We haven't finished filling out these matrices yet. Can you give me some numbers that'll work? 2 and 3? Like 2 and 3? Okay, add them up, you get 5, right? Subtract that from there. There you go. You've got a pivot, only 1 free variable, which means that the eigenvalue 8 fails to pull its weight. So these matrices are both diagonalizable, and these are not diagonalizable. Or this one is not diagonalizable. Okay? Clear enough? make sure, okay, so this was just on the test you took like less than a week ago, so I know you know it already, but make sure you know how to write down the matrix S and the matrix D. S inverse AS equals D. Alright, so you want to make sure you have that well in hand. Okay, let's take another kind of theoretical problem. Is everybody okay with that one though? So far so good? Alright. Let's try another theoretical example. Okay, so this will be part B. So I'm going to give you a linear system this time. So x prime equals, and it's also a 2 by 2, 2, negative 1, 2, 4, and x. Okay, and then here's what I want you to do here is I want you to classify the origin as a source, a sink, a saddle, a spiral, or a circle. So these are the different options of what this could be. And how do we do this? Remember? Find your lambdas, right? So you find your lambdas. So let's see if we can do that. We take the determinant of 2 minus lambda, negative 1, 2, and 4 minus lambda. And this gives me 2 minus lambda, 4 minus lambda, and then plus 2. And now this is just going to be a quadratic, right? So this, we only do this for a 2 by 2, by the way. We only talked about this for a 2 by 2. So we're going to get lambda squared minus 6 lambda plus 10, I think. I did my math right. And so how do I find my lambdas now? Yeah, gotta use the quadratic formula, right? This actually does not factor nicely. So you use the quadratic formula, I'm going to get 6 plus or minus the square root of 36 minus 40 all over 2. So this becomes 6 over 2 is 3. And then 36 minus 40 is negative 4. The square root of negative 4 is 2i, plus or minus 2i. And I'm dividing it by 2, so it's going to give me I here. Based on those eigenvalues, do you remember which of the classification types it will be? It's definitely a spiral, not a circle. Circle would have to have a 0 here. So it's a spiral, and does the solution spiral towards the origin or away from the origin?
Away from the origin.
Right, so a spiral out. That's because the solutions to this, when you write down the solution, the A part here, the real part, is going to be out in front of everything, right? So as t gets bigger, it's going to blow up. You know, you're going to have your vectors in here and everything with the sines and cosines. I'm not really reviewing that part today, the whole coiling it out as a FLOI, a foil. But you basically do that process and you're going to get something that spirals out as the t gets big. Okay, so it's an outward spiral. Okay, sounds good. Okay, let's do a couple more. Okay. Couple more here. These are fairly quick, so I don't mind taking a minute to do them. Let me know if you have any questions. So far, so good? Okay, so here's the next one. Assume, these are just kind of a random mix of problems here. Assume that A and B are 4 by 4 with, let's assume that the determinant of A is negative 2 and the determinant of B is 3. Let's compute the following thing. Let's find the determinant of the matrix BA B inverse times 3A times B inverse to the, B inverse transpose. Make sure I have transpose. This is just, we've been doing a lot of calculations of determinants lately, but we haven't done much that's been theoretical. It's all been just to find eigenvalues mainly, is what we use it for. But I want to go back. This is a chance to remind you in chapter 3, we learned about properties of determinants, like how they behave with respect to different things. So let's see if we can do this. Does anybody have a suggestion how we can start breaking this thing down? Yeah, I can find the determinant of each piece one by one and then just multiply them together. Right, that's the way you want to do it. Determinants respect multiplication, actually. So I want to find sort of the determinant of this part, and this part. I have sort of 3 parts here. We're just going to multiply them together. So can you remind me, what effect does a transpose have on the determinant of a matrix?
Nothing.
It doesn't do anything to it, right? What about inverse? Say again?
Yeah.
It's reciprocal. It flips it over, right? So if the determinant of B is 3, then what is the determinant of B inverse? Okay, so this part is 1/3, exactly. Okay, how about I'm kind of going from right to left for some reason. Let's take 3A here. So the determinant of A was 2, it was -2. So how am I going to get the determinant of 3A? Say again? Multiply by 3?
Oh, no, they're 4 by 4s, so it's...
Yeah, this is where you have to use the size, right? Because really, every single row of the matrix is being multiplied by 3. So you're going to pick up 4 factors of 3. 3 to the 4th is 81. And you're now multiplying that by whatever the determinant was originally, which was -2. So if you take 81 and multiply by -2, you get -162 for that piece. Okay? That makes sense so far? And then we have the first part here. So we have to figure out BAB and then flip it over. So what is the determinant of BAB when equal? Yeah, it's 3 times -2 times 3, right, which is -18. But then, because it's an inverse, I have to flip it over. So -1/18 would be the answer for that part.
Should we put a transpose on that one?
You transpose numbers? Transpose only applies to a matrix, right? So you wouldn't transpose, definitely don't need it. Yeah, so we'll just leave it like this. Now the 2 minus signs cancel. And I have 162 on the top, and I have 18 times 3, which is 54 on the bottom. So whatever that is the answer. These matrices are both invertible. So is this result, because none of those determinants are 0. Makes some sense?